Yeah, let's move on to the last topic, which is linear constant coefficient differential equation. So if you recollect, we have seen this topic in which chapter here? We talk about this topic in ah, continuous time Fourier series. So what did we say? We said that any LTI system, any LTI system which is relaxed, okay, so we say that relaxed system means what? The initial conditions are zero. So any LTI system, any relaxed LTI system can be represented as can be represented as linear constant coefficient differential equation as summation k equal to 0 to n a k d power k y of t by dt power k, which is equal to summation L equal to 0 to m bl d power l y x of t divided by dt power l. Okay, so any LTA system can be represented like this, but we know that LTA system in block diagram representation can be written as x of t is passed through the same LTA system, and this flow should have impulse response h of t, and the corresponding output is given by y of t equal to x of t convolved with h of t. Okay, so let us call this equation 1. So just to have clarity, let us call this equation 2. First let us focus on equation 2. Okay, so Fourier transform taking Fourier transform for equation 2, what do we get? Taking Fourier transform to equation 2, we get how is this looking at? Our output y of t will have y of j omega as the Fourier transform, and that should be equal to, note that this is convolution in which domain? Time domain, and hence what happens in frequency domain? That should be equal to x of j omega multiplied with h of j omega. By convolution in time domain is multiplication in frequency domain. Let us call this okay. Yes, from this what do you get? We get h of j omega to be equal to, so this implies h of j omega is equal to y of j omega divided by x of j omega. Okay, so h of j omega, we will talk about what is that. So this, let's call this equation 3. Okay, now let us apply Fourier transform for equation 1. Okay, so equation 1 has differential elements, so differentiation in time domain corresponds to what in frequency domain here? The corresponding Fourier transform will multiplied with j omega, will get multiplied with j omega. Okay, now what we will do, we will take Fourier transform. Okay, so taking Fourier transform for equation 1, we get, okay, so what is the property we use differentiation in time domain property. Okay, so we use differentiation in time domain property. So what do you get? You get summation k equal to, hopefully you have written equation 1, so I'll get summation k equal to 0 to n ak. So you have d power k y of t by dt power k, and hence you will get j omega whole power k y of j omega, which would be equal to summation L equal to 0 to m bl j omega whole power l x of j omega. Okay, so let us see why this is correct. Okay, where is our equation 1? Equation 1 is this one. Correct. So summation k equal to 0 to n ak d power k y of t by dt power k equal to this whole term. So if you take if you use differentiation in time domain property, what do you get? Here you have d power k y of t by dt power k. So if you take the Fourier transform, you get how much? J omega whole power k y of j omega. So that is what we have written there. So similarly here we have what? D power L x of t by dt power L. So if you take Fourier transform, you get j omega power L x of j omega. So that's what we have written there. Okay, so let me rub that so that there is no clutter here. Yes, so after taking Fourier transform, what did we get? We got this. So note that y of j omega on the left hand side we can take it out, and x of j omega on the right hand side we can take it out because they don't contribute to the summation. So this implies y of j omega multiplied with summation k equal to 0 to n j omega whole power k equal to x of j omega multiplied with summation L equal to 0 to m bl j omega whole power L. So here we should put ak. Okay, so now what do? We send x of j omega this side and this summation to the right hand side. So this implies y of j omega divided by x of j omega would be equal to summation L equal to 0 to m bl j omega whole power L divided by summation k equal to 0 to n ak j omega whole power k. Okay, this is L and this is k. Okay, so but if you look at our and let me call this equation 4. Now let us compare equation 3 and equation 4. What is equation 3 here? It tells that h of j omega equal to y of j omega by h of j omega. So from equation 3 and 4 we see that from equations 3 and 4, what do we see? From equations 3 and 4 we see that what is that we got finally? H of j omega which is equal to summation L equal to 0 to m bl j omega whole power L divided by summation k equal to 0 to n ak j omega whole power k. And what is this here? This is nothing but our frequency response. Okay, so this is nothing but the frequency response of LTI system. Okay, so what does that mean? Our impulse response h of t and the frequency response h of j omega, they form Fourier transform pair. So this implies h of t and h of j omega form CTFT pair. Okay, so CTFT pair. What does this mean here? So Fourier transform is there means what? Fourier transform is there means what? Okay, so I'll write down that nicely. So that is h of t has h of j omega as the Fourier transform. So h of t, which is the impulse response of the LTI system, has Fourier transform h of j omega, and we call that as the frequency response. Fourier transform exists implies what? Our h of t should be absolutely integrable. Okay, as h of j omega exists. Okay, as h of j omega exists, h of t should be absolutely integrable. So first Dirichlet condition, right? H of t should be absolutely integrable. Okay, h of t should be absolutely integrable. So what does this mean? First we'll write down that h of t should be absolutely integrable. Okay, that is what is that? Integral minus infinity to infinity, absolute integral. So you should take modulus of h of t dt should be less than infinite. But if impulse response is absolutely integrable, what does that mean here for an LTA system? Remember the second chapter, for an LTA system, if impulse response is absolutely integrable, what will happen? The system becomes stable. Okay, because Fourier transform exists, which is h of j omega, the corresponding h of t should be absolutely integral. But what is h of t? That is impulse response of the LTA system. So because Fourier transform exists, the impulse response should be absolutely integrable. But we know that if the impulse response is absolutely integrable, that should correspond to which system? That should correspond to LTI system. So this implies the corresponding LTI system. Okay, so the corresponding LTI system, is stable. Okay, so corresponding LTA system is stable. Okay, so that corresponding LTA system is stable. So okay, so we got a differential equation, linear constant coefficient differential equation, and from that differential equation, what did we get? We have found out the frequency response of the system, and impulse response of the system and frequency response of the system, they form Fourier transform pair. Because Fourier transform exists, definitely the impulse response should satisfy the first Dirichlet condition, which is absolute integrability. So, but we know from chapter 2 that if any impulse response is absolutely integrable, then that should correspond to a stable LTI system. So that is where this process flows. So from differential equation, we proved that the corresponding LTA system is stable. Okay. So we are talking only about what system? No, once you say frequency response of the system, then we are talking only about which system? A stable LTI system. So what is that? Whatever we have seen till now, what does it say? So note, what does it mean? The frequency response. Okay, so frequency response of an LTI system exists. Okay, frequency response of an LTA system exists only if the system is stable. Only if the system is stable. Okay, only for stable LTA system we can do frequency analysis. Okay, so that is important. So what happens if the system is unstable? We will see that. So we have one more guy who is Laplace transform. So hopefully now you understood why should we study Laplace transform. In control systems, what you will study? You don't study Fourier transform, you study only Laplace transform. Why? Our control system can become unstable, then Fourier will not help us. Who will help us? Laplace will help us. Okay, we'll talk about that later. Okay, yes, so what is that we have seen from the differential equation? Correct. So we got the frequency response of the system in this way, which is given by this equation, equation 4. Okay, but we know that the output of the LTA system can be written in terms of convolution, and from that also we got the frequency response. So in that way we equated equation 3 and 4 and we got the equation. Let us call this to be 5. We got the equation 5. Okay, right. So that would be the frequency response of the system. So once I say frequency response of the system, that implies we are talking about which system? A stable LTI system. Okay.